Look around any modern city, and you'll see a massive, ceaseless demand for power. Hospitals running life-saving equipment, heavy industries manufacturing steel, and homes lighting up at dusk, they all require an uninterrupted flow of electricity. To meet this immense physical hunger, engineers harness energy from a counterintuitive source, the smallest building blocks of nature, the atom. The starting point for this microscopic energy is a radioactive element called uranium. Before it ever reaches a power plant, it has to be physically blasted and scraped out of the earth in deep underground mines. The extracted raw uranium is processed and compressed into tiny, uniform cylinders known as fuel pellets. These are stacked inside long metal tubes called fuel rods. Thousands of these fuel rods are then clustered together to form a massive geometric grid, the reactor core. The sheer scale of modern human infrastructure, every glowing skyscraper and humming factory, is supported by the dormant energy trapped inside these highly organized clusters of radioactive rock. Inside that core, we trigger a physical process called nuclear fission. It starts when a single rogue subatomic particle, a neutron, is fired into a uranium-235 atom. The impact forces the heavy atom to violently split apart. The exact moment that atom breaks, it releases two things: an intense burst of thermal heat and several new free-flying neutrons. This diagram illustrates the mechanics of what happens next. Those newly freed neutrons act as projectiles, striking neighboring uranium atoms. One split causes two cause four, creating a continuous repeating cycle known as a chain reaction. Left completely unguided, this exponential multiplication occurs in fractions of a second. Without a way to manage the sheer volume of splitting atoms, the reaction would rapidly overheat and become a severe physical danger. Looking back at the network path, you'll see solid vertical lines sliding down to intersect the connections. These represent control rods, the primary safety mechanism designed to tame that exponential growth. By lowering these metal rods directly into the core, plant operators can physically absorb the excess flying neutrons. This perfectly dictates the speed of the fission process, dialing the intensity up or down as needed. A nuclear reactor functions as a carefully balanced, highly monitored environment. It sustains the fission process just enough to produce a steady, continuous source of heat. To capture that steady heat, special liquid coolants are continuously flushed through the reactor core. The fluid absorbs the extreme atomic temperatures and carries them away to a separate chamber called a heat exchanger. Inside the heat exchanger, this transferred thermal energy meets ordinary water. The extreme temperature forces the water into a rapid physical state change, causing it to violently boil and generate highly pressurized steam. This dense, upward-rushing steam is then blasted directly against the stacked, heavy blades of an industrial steam turbine, forcing the massive rotors to spin at thousands of revolutions per minute. Connected directly to that spinning turbine is the generator. As the shaft rotates inside this heavy industrial housing, it spins wire coils through intense magnetic fields, converting that mechanical rotation into an electrical current. Every stage of this massive mechanical conversion, from the heat of the core to the rotation of the generator, requires meticulous, round-the-clock oversight from human operators monitoring thousands of metrics. The deep complexity of a nuclear plant, with all its heavy shielding and atomic physics, ultimately serves one simple mechanical purpose: boiling water to spin a wheel. Before that freshly generated electrical current can leave the facility, it has to be prepared for long-distance travel. Step-up transformers take the output and drastically increase its voltage, pushing the electrical pressure high enough to survive the miles ahead. The electricity then flows out onto the national grid, surging through endless lines of transmission towers that stretch across the landscape, bridging the gap between the isolated power plant and human civilization. Back at the start of that massive chain lies the silent, glowing blue water of the reactor core and the radiation it produces. To protect the outside world, engineers encase that core within multi-layered containment systems. Thick steel vessels and dense concrete domes keep all radiation permanently locked away from the surrounding environment. That secure containment allows the energy to safely reach its final destination. It flows out of the grid, stepping down in voltage, until it is used to light up our city skylines, run our local schools, and power our hospitals. Through heavy engineering and microscopic physics, we extract the dormant power of a single atom and use it to safely illuminate the lives of millions. If you found this breakdown helpful, hit the like button, share it with your friends, and let us know what topic you want to see covered next.